Hey 301ers, welcome to the first video in Module 3, where we'll be examining how we utilize fats for energy. Up to this point, as we've been looking at glycolysis, we've been discussing carbohydrates. And we need to look at carbohydrates just one more time before we enter into our discussion on fat. And that is, how much energy can we actually get out of the stored carbohydrates that we actually have in the body? Looking at this figure, there's an extremely happy picture there. And I can only assume that he's happy because he knows he has a rich storage of glycogen in his body that he can use for energy to support his baseball needs. If we start out over here, we see that he might be storing about 400 kilocalories of energy just by the glycogen in his liver. And we have an additional storage spot in our bodies that we utilize through our muscle tissue that gives us about 1,600 kilocalories worth of energy, and we have a minuscule amount that we can utilize from the circulating glucose that's in our plasma. Do all the addition here with all these numbers, and you get approximately 2,000 kilocalories worth of energy out of our carbohydrate stores. And if we put that on this handy dandy little figure I made, that's where it shows up on the scale that goes from 0 to 100,000 kilocalories. Why did I create a scale that goes up to 100,000 kilocalories? Because that's the amount of energy we get with the fat stores that we have in our body. So at first glance, I bet you thought 2,000 kilocalories was actually pretty decent. A typical person perhaps ingests about 2,000 kilocalories worth of energy a day. And here, just in the amount of glycogen we store, we can support 2,000 kilocalories worth of energy requirements. But if you are able to metabolize all of the fats that you have in your body, we're talking more like 100,000 or more, depending on how fat you are, kilocalories worth of energy that you can obtain from that fat tissue. Amazing, right? So surely, if we can tap into those stores, we can get a lot of ATP to support our movement needs. Let's take a look at this a little bit closer. Glance at this for a second and think about, what is it that you're looking at? For one thing, you have a backbone here, and you have three what look like fairly identical molecules here stretching out from the backbone. If you haven't thought about it yet, this is a triacylglycerol, also known as triglyceride. I think we've discussed that before, but I'm going to call it this because it makes more sense in explaining to us the structure that we're actually looking at. So the backbone here is actually the glycerol. And then here are three little branches that are coming out are our fatty acyl groups. These are called fatty acyl groups because they are attached to something here. They're attached to glycerol. I'll explain this in a second. Now, as we have these fatty acyl groups, go ahead and write that, fatty acyl groups. We have three of them, right? Triacylglycerol. We have them attached to glycerol here, but in this form, this is really only good for us in the sense of storage. We can't really utilize these in producing energy until we break these bonds here and we release these fatty acyl groups into the bloodstream. Okay, and that's what we call lipolysis. And when we go through lipolysis, let's go ahead and write that down, lipolysis. When we go through lipolysis and we break off these fatty acyl groups, there's a special enzyme that allows us to do that. This enzyme is called hormone sensitive lipase. Lipase, an enzyme that breaks down fats. Okay? So here we are going to be breaking off these fatty acyl groups, and as we break these bonds, we're going to be replacing this glycerol with a hydrogen, just so we're nice and happy, and that's when we get fatty acids. We get these fatty acids that are free. So the free fatty acids then are released into the bloodstream, and they are going to be transported to the muscle, where we are going to continue the process of something called beta oxidation. A lot of complex words here, and whenever you see a process like this, I don't know about you, but I tend to freak out a little bit. I'm like, wow, there's a lot of stuff to know there. Don't worry, we're going to simplify this quite a bit, as I usually do, because I think simplification of complex processes is really good for helping us understand what's really going on. So you heard me talk about before the fatty acyl groups, right? Those fatty acyl groups were called acyl groups because they were attached to the glycerol. But then we released them and had them transported through the blood as fatty acids. Those fatty acids are going to be taken into our muscle cells. So those fatty acids go into our muscle cells. And when we get inside the muscle cells, that area is called the cytoplasm, right? The cytoplasm, or specifically if we're talking about muscle cells, talk about the sarcoplasm. Those are synonymous. Muscle's cool because it gets all these specific names because it is just that awesome. So once we get into the cytoplasm or sarcoplasm of our muscle cell, we need to be able to get that fatty acid into the mitochondria. The mitochondria is where we're going to break this down, and you'll see why in a few minutes. But for now, we need to be able to get this fatty acid into the mitochondria, and it just can't cross through the mitochondrial membranes. We have to be able to transport it inside, and this is a bit more of a complex process as well that you can learn in a later time if you take a biochemistry class. But for now, we're going to know how we do this very simply by we take those fatty acid groups and we're going to activate them by adding a CoA to them. And since then we're going to remove that hydrogen. Remember before we took that oxygen and we added a hydrogen to it to create a free fatty acid, we're going to go ahead and remove that, and we're going to add a CoA to it. And therefore we go back to calling it an acyl. So now we have acyl CoA at this particular point, and now we've activated that fatty acid so that we can continue on through the process of actually getting some energy out of it. Now here are some things to take note. You've seen these before. You've seen FADH2, and you know it goes to the electron transport chain, and you see NADH plus H plus. You know that also goes to the electron transport chain, and we're getting these because we are oxidizing this process and stealing those electrons from the structure changes that are occurring in beta oxidation, and we're also going through hydrolysis because this process requires water for it to occur. Now the last thing I want you to take note of is you see an acetyl-CoA here, and you remember acetyl-CoA enters the citric acid cycle where we're able to get a whole bunch of further ATP out of that process. So what we're going to do here is we're going to do a little bit of drawing here, and I'm going to first note what molecule this is. This is what we call stearic acid. This stearic acid is a fatty acid that has 18 carbons. 18 carbons. Where are these carbons? I'm going to show you. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Easy, right? These right here are oxygen. The red parts here are oxygen, and we have another hydrogen on the end here. So this is a fatty acid, right? But when we activate this, we're going to change this end product by adding a CoA here. And when we add that CoA, we're activating this fatty acid so we can further go along beta oxidation. So at this particular point, it's a little bit more complex than I would like to look at it here. So how do I want you to do this? What I would like you to do, or at least what I do to sort of simplify this, is I draw it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 carbons. Okay, so this is how I draw it, just those simple squiggly lines. And it looks sort of like what we just saw, but I can't draw that other figure, so simple lines it is. Now, what are we going to do with this? We have a long acyl-CoA now because we've attached CoA to it, and we've essentially gotten ourselves ready to go through beta oxidation. And by the way, this process here, by priming the fatty acid with this acyl-CoA, is not free. It costs something. For us to attach this CoA to the end actually costs us -2 ATP. For us to do that, it actually costs us some energy. Okay, so now we started a system that instead of giving us some energy, we've already taken out 2 ATP. We've heard about something like this before, right? Glycolysis. That's all right. It's a small investment to pay for all of the ATP we're going to get out of this process. So this is activating our free fatty acid. We add the CoA to it. Now we have acyl-CoA. It is considered activated. We can now transport this into the matrix of the mitochondria. And that's where we're going to do the citric acid cycle and the electron transport chain. Okay, so let's see how we actually do this. So, when we have this activated fatty acid, we're going to need to make some cuts here. We're going to chop it up. Now, what I like to tell people to help them sort of remember what goes on here, when we activate this fatty acid by utilizing these 2 ATP to create acyl-CoA, we're going to be chopping this free fatty acid up, and I like to think about doing that with a pair of scissors. And before we can get started with this process, we need to purchase the pair of scissors. Okay, so with this 2 ATP, that's like my money I'm using, I just purchased these scissors. And what I'm going to do is I'm going to be making cuts with every 2 carbons, right? So 1, 2, I'm going to make a cut here, and I'm going to make a cut here, the next 2, and a cut here, and a cut here, and a cut here, until I go all the way down the chain. Now, if you look at this, we made 1, 2, 3, 4, 5, 6, 7, 8 cuts. Now, here's the beauty of where we get all of our ATP. When we make 8 cuts, every time we make a cut, we get an NADH and an FADH2. So we made 8 cuts, correct? So we have 8 NADHs and 8 FADH2s. Why are we doing this? Well, for one, we know we're going to get some ATP out of that, right? Let me be correct here. We get NADH plus H plus. And what we're going to be doing here is this part that we just cut off. So we cut this off, and this part here is going to sort of float off. And in this particular case, when that floats off, we actually now have an acetyl-CoA. You should exactly know why that is important. Remember, that's how we get into the citric acid cycle. So how many did we end up with? Well, here's 1, here's 2, here's 3, here's 4, 5, 6, 7, 8, 9. At first glance, you might have said 8, but no, we have 9. And the reason that we get 9 and not 8 is because when we make this last snippet here, we're going to have this one float off, and we're going to have this one float off. That's 2 acetyl-CoAs on that last cut that we make. Every other one, we only get 1 out of it, right? We got 1 here, we got 1 here, we got 1 here. But this is the last cut. So essentially, we only have 2 left. We're going to cut it right down the middle, and that's how we get 2. So with 8 cuts, we get 9 acetyl-CoAs out of this 18-carbon fatty acid. Let's make up some tallies here. Remember that when we have 8 NADHs and we run those through the electron transport chain, how many do you get for each NADH? How much ATP? You get 2.5. Okay, let's go ahead and just talk about FADH2 while we're at it. How many do you get out of that? When you run it through the electron transport chain, you get 1.5. Okay, I didn't prepare for this, so let's do some math. So 8 times 5 is 40, and then 16, so we get 20 here. And here we get the same thing, 40, 8, 9, 10, 11, 12. So right here, if we look at what we just did with the NADH and FADH2s, we get 32 ATP. And when we look at acetyl-CoA, if you go back and look at our module on acetyl-CoA, if we run that through the citric acid cycle and count everything up, remember we get 1 substrate level phosphorylation out of it, so 1 ATP from the GTP, and then we get 3 NADHs and an FADH2. If you add all of that up, you get 10 ATP every time you run the citric acid cycle. You get 10 ATP out of that. So 9 times 10 is 90. We add all of that up, we get 122 ATP. Oh, but we're not done yet. Remember, we had a small investment at the beginning for us to make all of those cuts. That was 2 ATP. We need to factor that in. So minus those out, and we end up with a grand total of 120 ATP as we break down 1 stearic acid, which is an 18-carbon fatty acid. Now, you should be getting the hang of when I do a drawing like this, I'm going to be expecting you to be able to do it. Now, when we talk about fatty acids, we're talking about these even-chained fatty acids. Maybe you'll get an 18-carbon fatty acid. Maybe I'll ask you about a 16-carbon or a 14-carbon or a 22-carbon. Oh my, there's so many choices. But if you are able to understand how this process works, it doesn't matter what number I give you. You should be able to figure out how much ATP you get out of it. All right, guys, hope you enjoyed this video in Module 3. I'll see you in the next video.